Okay, good afternoon. My topic for this afternoon, guys, is the last topic on integral calculus. It will be the computation of volumes, regular and irregular volumes. This will be my last topic on integral calculus before I will proceed with the topic differential equation. Okay, let's proceed. This is now lesson number 60 on my channel, the topic on integral calculus, volumes. The computation of volumes got so many variations. So for this afternoon, I will discuss what you call this case number 1 on how to compute volume. Case number 1 is actually circular disk method. This is a solid with no hole. Circular disk. It's a round thing and it got no hole inside. So I place it here. It is solid, no hole. Okay, let's try to bring out or try to see the configuration on the Cartesian coordinate system. Y-axis, x-axis, okay? We are given a curve. This is the curve. The equation is y equal to a function of x. This equation is actually something like it's almost parallel with respect to the x-axis. It's not a straight line. It is a curve, okay? But it could be a straight line. So meaning in general, y as a function of x, it could be a curve or a straight line. This is the curve. Okay. The first boundary is x equal to a. Second boundary is x equal to b. Meaning x equal to a with respect to the y-axis, x is actually a. You have seen that this is a straight line here, is x equal to a. The one on the right is x equal to b. It's still a straight line. Straight line, straight line. This is a curve. This is the y-axis. The requirement for the computation of volume is that actually the differential area, we must have to rotate that differential area with respect to x-axis or y-axis. It depends on the orientation of the problem. Okay? For case number 1, the differential area is to be rotated with respect to the x-axis. This differential slice here, we try to rotate it along the x-axis. It got no holes. Okay, it's a solid thing. And the requirement is if we try to rotate the shaded line represented by the cross lines red color, okay, if we try to rotate this along the x-axis, the requirement is what will be the volume. As you try to see, the volume is actually irregular. In reality, it could be what you call this, a regular volume or an irregular volume. It depends on what will be given on the problem. So in general, I place it y as a function of x is actually a curve. It could be a complicated curve or it could be simply a straight line. Okay. Let's try to bring out the volume if we try to rotate this horizontal slice or vertical slice rather with respect to the x-axis. We try to rotate this one. Okay. I place it here now. Differential volume will be formed when differential area is rotated. So for case number 1, if we try to rotate the differential area with respect to the x-axis, okay, this will be the configuration on the isometric view. Okay, sorry guys, when I was teaching in college, I used to, what do you call this, teach also drawing number 1. It's the basic drawing, so I could draw an isometric drawing. This is an isometric view of this horizontal, this vertical slice. If we try to rotate it with respect to the x-axis, okay, it's a disk, right? It's a round thing. okay, with a certain thickness. So if we try to rotate this one with respect to the origin, this is the radius, okay, and the radius is represented by y higher minus y lower. This actually represents the radius, okay. I will not call it height because we are discussing a round thing, so I think it is appropriate to place the designation of this height here to be radius instead of height. This height here, okay, is variable. It is y higher minus y lower. It is the ordinate at this point here minus the ordinate at this point. And unluckily, the radius is actually variable as the differential area moves from x equal to a until x equal to b. That radius is actually variable. It's not constant because the given configuration is just y as a function of x. We don't know yet if it's a straight line. If it will be a straight line, we are lucky, okay? If it will be a curve, we are unlucky. Okay, let's bring out case number 1. If the circular disc is to be rotated with respect to the x-axis, this will be the configuration. For case number 2, if the circular disc will be rotated along the y-axis, this will be the configuration. The resulting radius will be xr minus xl. You replace this yh here by x, and this is x also. If we try to rotate it with respect to the y-axis, and the thickness will be dy. Okay? So let's try to bring out the general equations on how to take the area if it falls under case number 1 or case number 2. For case number 1, okay, if the circular disc is to be rotated along the x-axis, okay, differential volume. Okay, we are now bringing out the differential equation on how to compute for the volume. Differential volume is equal to pi times the quantity y higher minus y lower quantity square times x. How come it is like that? Okay, the derivation is something like this. If we got a circle, okay, and the radius of that circle is actually y higher minus y lower, okay? Okay? The area represented by the circle here, area is actually pi r squared, right? So if this circular disc got a certain thickness, okay, to compute for the volume, okay, volume will be area times thickness, okay? Therefore, volume now, the thickness is actually dx, okay? So what will come out? Differential volume now will be equal to area, which is pi, and what will be the radius? Radius is actually the difference y higher minus y lower. Y higher minus y lower quantity square. This represents the area. So to compute for the volume, take this area here, okay, times the thickness. This is multiplied by the x. And this formula here is actually this. You got it, guys? So actually the first part is the area times thickness. Volume in general is area times thickness. If there is no hole at the middle, okay? There's no hole. Okay? I place it here. Y higher will be a function of x. Y lower will be g of x. And luckily, if the differential area is to be rotated along the x-axis, y lower is actually 0. Okay? It's 0. It's an equation of a horizontal line along the x-axis. It is y lower is equal to 0. So you don't have any more problem on how to compute for the equation of y lower. Y lower is 0. That's the equation. If the differential area is to be rotated along the x-axis. Radius is actually y higher minus y lower, and thickness is equal to dx. That is for case number 1. For case number 2, when the area is to be rotated along the y-axis, okay, differential volume will be equal to pi times the quantity xr minus xl quantity square, and the thickness now will be dy. It is same as this. Okay, it will be still similar to this, but the radius now will be xr minus xl, and thickness is equal to dy. Therefore, differential volume is equal to pi r square, pi times xr minus xl quantity square times dy. And this is the general equation on how to take the volume of a circular disc rotated with respect to the y-axis. It is this. Okay. So this is actually the differential equation under case number 2. This is under case number 1. For case number 2, supposed to be, we are given xr as a function of y, xl is g of y, and luckily, for if the area to be rotated is actually will be rotated with respect to the y-axis, xl is equal to 0. It's the vertical line, xl is equal to 0. And the radius is xr minus xl, and the thickness is equal to dy. Same configuration, we just replace y higher by xr, y lower by xl. Because the first one is to be rotated with respect to the x-axis, okay? And the other one is to be rotated with respect to the y-axis. So in the computation of volume under integral calculus, if the required volume is irregular, this is the general equation. Whether irregular or regular, this will be the formula. If it will be regular, okay, the equation will not be as complicated, will not be complicated compared to the irregular. So we are lucky if the resulting equation will be not a complicated equation. But if it will be a complicated equation, that's another thing. Okay, like this one here. If we try to rotate the volume under the limit x equal to a, x equal to b with respect to the x-axis, okay, as you notice it, the function is actually variable. Okay, so it will be an irregular volume. Okay, if it comes out to be a straight line, that will be a regular volume. It will be much easier on how to compute for the volume. But whether complicated problem or not complicated, this will be the required formulas. Differential volume for case number 1 will be pi. The radius will be y higher minus y lower quantity square times dx. And for case number 2, differential volume is pi. The resulting radius will be xr minus xl quantity square times dy. Pi r square is area times thickness, that will now be volume. Since this is dy, the thickness is just dy, this is not yet the total volume. It will be differential volume. Okay, guys? That's the concept on how to compute for regular and irregular volumes under integral calculus. So the next time around, on my next lesson, I will give you examples on how to compute volumes. I will give you an example for irregular volume. We will derive the formula on how to take the volume of a cylinder. We will derive that one using integral calculus. Okay, good afternoon, Los Angeles.